Hi everyone. Hi. Can you get some coffee and have a seat? We'll start in about 1 or 2 minutes.
Yeah.
Thanks. Where's Thomas? It's really nice to see so many people here, and I'm really glad that we could actually use the Center for Astrophysics in part for this year's Harvard-Heidelberg meeting. The other place that, well, oh, by the way, sorry, I'm Alyssa Goodman. I know almost everybody here, but not everybody. I'm going to turn this over to my fellow organizers in just a second. But before I do that, I just want to do something unusual. Usually thank people at the end of the meeting, but you should know that the people who put all of this together for you are really the local organizing committee. Could you guys all stand up, please? Okay. So here we go. We have Hope Chen, Anna Rosen, Catherine Zucker, Blakesley Burkhart, my co-chair here, and John Forbes back there, and Sarah Block, who we've gotten a lot of messages from probably. So anyway, they have done everything, and not only is it important to thank them so much, but also they are your local guides, because you can sit down now. We're going to be walking to a facility across the way called Pforzheimer House, which is one of the houses at Harvard. So Harvard has like Hogwarts, okay, a house system, except there's 12 of them. And anyway, so one of them is just across the way here, and we're going to use their facilities. I'm lucky enough to be associated with that house, so that's how we get to do that. And they're very accommodating. So if when we're over there you need anything, ask me, and I'll ask the housing staff, okay? But for now, I'm going to stop for a moment and turn it over to Thomas Henning, who's going to explain the origin of the Harvard-Heidelberg meetings. And don't worry, we'll get to logistics after that.
So now you get a 1-hour history talk. So it's very nice to be back to Harvard and to have another edition of the Harvard-Heidelberg meeting. It actually started at a sunny afternoon in an Italian restaurant in Heidelberg. So we had a great late lunch, and then we were chatting about the good old times. And the good old times actually started in California, where there was a group of people coming together and to have regular star formation meetings. It was mostly Santa Cruz, Berkeley, and NASA Ames. And then later, I also learned that this series of meetings actually continued with meetings between the East Coast and the West Coast. And then at some point it died. And then I calculated flight hours between Frankfurt and Boston, which is of the order of 6 hours, which is very similar to Boston, San Francisco. And then I thought, why don't we start joint meetings between Harvard and Heidelberg? And obviously, these two places are large centers in their respective countries doing star and planet formation. But it's not only star formations, also there's a very nice connection to astrochemistry. I just learned statistical analysis of data, which is getting close to my heart now because the exoplanet field. And I see a person who's interested in dust and extinction laws, and we have a lot of connections. So in fact, we also, over the years, we now have seen that people spent some time in Heidelberg. Eric is here. He just talked about the last winter visit. But we also have, of course, exchange of former students and postdocs, and I hope that will continue because one of the ideas for the meeting is that you become familiar with the work, but you also start to think about joint projects and then exchange your ideas and then get interested. Maybe you go also to the other place for a while and work over there. So that is how the meeting came about, and I'm really looking forward. It's also a possibility to trigger a staff formation meeting at your place. I don't think that you have more than one per year, so that's good. And I hope you have a productive meeting with a lot of discussions. And let's now start the game. And of course, I should also thank the local organizing committee, but I wanted to do that at the end.
All right, so welcome everybody. First, I just want to say we have a very special gift for you. You've come all the way to freezing Cambridge in November. We have a special Harvard-Heidelberg Star Formation 2017. We call these beanies. Okay, stay with me. Beanies. Yes. So please pick up one. They're for you. There's a big stack of them right here. I just want to give a very quick kind of overview of the next couple days. You'll notice on the program there's several different types of talks and events we're having. There's something called a framing talk. These are a little bit longer, which combine introduction to a subject as well as someone's personal research. So those are a little bit longer with a longer sort of discussion time afterwards. Everyone is giving an introductory talk. So those are 2 minutes, and those are a quick way to introduce yourself, say what you're interested in, what you're currently thinking about, your research. And so if you don't see your name somewhere on the program over the next 3 days, just let one of the organizers know. And then there's highlighted research talks. Those are 15 minutes total, and those are, as it sort of suggests, highlighted research. And then we have unconference sessions, which probably sounds a little strange. So Alyssa will be telling us more about what those are in a second. So this morning, we've got the full range of these different activities, different sorts of talks. At 10:40, we're going to walk over to FOHO, so the other building that we're going to be in, where we're going to have the coffee break and the unconference sessions. This building is actually, I think, one of the more picturesque on the Harvard campus. This is the Radcliffe Quad. So we'll actually be in these rooms here. And if you get lost, just know that it's very close. I don't know if this is going to actually help you, but if you just walk down Linnaean 1 block and turn right, that's where we're going to be. So it's a very close walk. If you have your beanie on, you'll be warm. It's not that far. Okay, so just 2 action items for you. Please, and Alyssa will explain this more, think about the topics for the unconference discussions. So what sort of research topics that you might like to lead a discussion on, and we'll have a vote on those topics. And then if you're giving one of the 2-minute talks, then please email your slide to the conference email. Now the last point is that we're going to have a conference dinner.
Hey!
It's on Tuesday night. It's at St. Philip's Bowling Haven. Professor Finkbeiner is demonstrating what we'll be doing. It's a very lovely place. It has flatbread pizzas, which are delicious. It has a huge beer list. And candlepin bowling. It's candlepin bowling. It's a very special place. So it's going to be a lot of fun. So thanks for coming, everybody.
You can show the one where I got a stripe.
Yeah, so as I was explaining at dinner last night, candlepin bowling is harder than regular bowling. So anyway, and it's a very, very New England thing. If you don't have one of these handouts, I'll just pass them around, and so you need one to follow what I'm going to be saying. If you already took one, never mind. And if you don't have a schedule, there's more of those in the front. Okay, so to add a little bit to what Thomas said, when we were having this 4-hour lunch, we also thought that what would be really great for a meeting would be an unusual meeting where people could really spend more time talking to each other than talking at each other. And so what an unconference is a sort of somewhat orchestrated conversation that's supposed to be kind of one level more formal than just talking to someone in a restaurant, okay? But several levels less formal than giving a talk, okay? And so the way to arrange for this to happen, if you look here, this is what's on your handout, and it says, what is the goal of an unconference? And you can read that later to get an even better idea of what we're talking about. But operationally, the way that this works is over here, we have a picture at the end, thank you. So in the corner of the room here, we have these blank pieces of paper that have a grid on them, and it says idea, share, and votes, okay? So what happens is, as you're thinking about what you might like to talk about with the people who are here, you just write down what your idea is. So, you know, I'll just pretend this is a conference about something else. I want to talk about aliens on Venus, okay? And so I write aliens on Venus, and then I write my name here because I'm the one who proposed this crazy topic. And then later, across the street at coffee today, what we're going to do, so please write some ideas if you can before we go across the street, just quickly, because this morning we have this weird logistics where we have to do it very quickly. We'll do the ones for the future with a little bit more leisure. I'll explain that later. But anyway, so you write down your idea, and then other people during coffee will put just a little tick mark. If you're interested, just put a 1, you know, next to the topic you're interested in. And I made space for 5 things here. We have 4 rooms. We could actually somehow do 5. We could do 3. 2 would be way too few because there's too many of us, okay? So we can either have 3 or 4 or possibly 5 unconferences at the same time. So just think about something that you would like to talk about, probably not aliens on Venus, okay? But don't say massive star formation, okay? That is not a specific enough topic to have an hour-long conversation about, okay? So, you know, you could say radiation pressure modeling and adaptive mesh simulations of massive star formation. That's okay, but don't say massive star formation, okay? So anyway, and it can be as usual or unusual as you want. And then when you're in the session, the idea is for people mostly to just talk. It's perfectly fine for people to show images or calculations or whatever. We'll have blackboards and whiteboards. If people want to show slides, they can show 1 or 2 slides unless the audience says, oh, please, not the audience, the group says, please show more, okay? But please, if somebody is starting to give a talk, just channel me and make them stop, okay? And so we really just want to have a conversation. And then whoever the chair is, please get someone else in your room to agree to be the so-called recorder, and that person should write down what happens. And so right here, by the way, if you don't have a flash drive with you, there's a Scratch directory on Google Drive, so you can just throw stuff in this directory. It's linked from the handout, which is also linked to the schedule here somewhere. I can't see without my glasses, but it's there.
It's in the bottom of the box.
The bottom of this thing?
Yes.
Okay. No, that's the suggestions. I meant the Scratch drive, the instructions.
It's in the links to the main handout.
Yeah, so somehow there's a link from this to the unconference handout.
Unconference plans right there.
I believe you. Okay.
There's a link.
Yes, here, I can see this. Okay, so that's, if you click there, you can get to the link with this Scratch directory. Okay, so that's just for if you want to show some slides, and then the person who's the chair will have their laptop hooked up in the room. Okay, and then the recorder will please take notes in preferably a Google Doc. You can use something else if you want, but when you're done, just email what you've done to this email address for the meeting, and then at the very end of each day, we're going to have like a recap of what happened in all the unconferences, and the person who's the chair is going to be asked to just explain. And it's very short, and it's just because what will happen, you'll see, is that people will want to go to all the unconferences, and you can't. And so the idea is just to find out what you might want to talk about more the next day, and so we don't plan these very far in advance. So right now, it's more important to plan the morning ones, and the afternoon ones, if the morning one gets filled up, you can just write your thing on the afternoon one. But we want to not plan them in advance because we want to see what people talk about. want to talk about as the meeting goes on. Okay, I think, all right, the notable exception is sometimes, and I know of at least one for this meeting, people want to do tutorials about a particular technique or a software package or an analysis package, and if you want to do that, that's fine, but just label it as a tutorial so that people will know that it will be actually a presentation, and that's totally fine. Okay, so a lot of people have been to these meetings before, and so you kind of know what I'm talking about, but is anybody totally lost and has a question, or just have a question? No? Is that it, Blakely? Should I proceed? Okay. So, our chair is Karen Oberg here, and you want to put my talk there? And so, our brilliant organizing committee had me give the first introductory talk, so I will now do that. And then there's 3 more introductory talks? Okay.
Including sharing myself, if I saw it correctly.
Yes. Oh, yes. Oh,
that's perfect.
I'll keep myself on time. I'll be harsh to everyone, including myself.
9:15, and it's supposed to be 9:15?
Yeah, perfect.
Right.
Okay, starting
I
now.
will take no more than 2 minutes to tell you, okay, that if I were going to give you a talk, which I'm not, I would talk about some of the things that I talked about last month at Cornell. So I gave these 2 big talks at Cornell where I had to explain kind of everything we were working on in a week to the people at Cornell. And if you really want to see what I said, all my slides are on my website. And so this is the cover page of one of them, and then I'll show you the cover page of the other one in a minute. But basically what I said is there's no such thing as a dense core. Okay, and I said that I believe that this emphasis on filaments that started, I don't know, half a decade or so ago, I thought was silly at the time, but I was totally wrong. And I think actually it's really important, and that what's going on is that we had a very unresolved view of star formation, and that now that we have high resolution and much better computer simulations, these things are coming into agreement, and it really looks like there's this kind of tangled mess that's some sort of turbulent process controlled by gravity and magnetic fields that eventually makes overdensities, that eventually make stars, but that those are not long-lasting entities, and that a lot of them, in fact, are pressure-bound. So this is just 2 snapshots of 2 recent simulations showing what I mean. This one came out a little low resolution. But anyway, in this one, is Alex Lazarian here? No, see, because I put this just for him. Okay, so you'll hear more about this in a little while from Hope Chen and from Blakesley in terms of what I mean by no such thing exactly as a dense core and the role of magnetic fields. So the other talk I gave was about the skeleton of the Milky Way and how we can use all kinds of long filaments, most notably these bones that Catherine and others will talk about more during the meeting, to try to reconstruct a better picture of the Milky Way. And in this case, so I think Kara Battersby is also coming, and they will tell you much more, as will, I hope, many of our Harvard colleagues. And just to advertise the tutorial that we will do, that's about this glue link view data visualization software. And if you don't get to go to the tutorial, ask Hope Chen, who's right there, or Catherine Zucker, who's right there, or me, and we will tell you more about it. 2 minutes and 10 seconds, I'm sorry.
No.
Oh, shoot, that's not mine. Right. I'm so used to doing that. Okay.
I will let the LOC fix it, but in the meantime, we will have Antonia, me, Hans, and Victor. So I guess, where's...
You want to go first, maybe? Or no?
Well, whoever is...
I have all of them up.
Yeah, so why don't you go? Perfect. Okay. So please go ahead.
Thanks. Good morning. So my name is Antonia Alkitic. I'm a postdoc here at Harvard. And today I would just like to tell you a little bit about the work that I was doing on giant star-forming clumps in simulations of high redshift galaxies. So the motivation for this work comes from observations, of course. So at high redshift, we see that star-forming galaxies often look very messy. Their morphology is dominated by a few very large star-forming clumps. And the sizes of these clumps are typically a few hundred parsec or up to a kiloparsec, and their masses are estimated to be between 10 to the 8 and 10 to the 9 solar masses. And it has been proposed that these clumps may be very important for the dynamical evolution of their host galaxies, because they, if they are gravitationally bound and long-lived, they might form star clusters of high mass that may sink to the center of their host galaxies due to dynamical friction, and maybe help form the bulge and other interesting things. So we decided, and some simulations do actually see that. So we decided to test this using the FIRE simulations. So the FIRE stands for Feedback in Realistic Environments, and it is a suite of high-resolution cosmological zoom-in simulations with an emphasis put on modeling the stellar feedback in great detail. So our results show that most of these large clumps are not gravitationally bound. They do not live long times. Typically, we see that they get disrupted within like 20 or 50 million years, mostly by their own stellar feedback. We don't see this evidence of radial migration just because they live such short lives, so they don't get to move much. And in terms of their star formation efficiencies, they're very similar to GMC, so they're not significantly more efficient at forming stars. So yeah, these are basic conclusions.
Thank you.
Sure. My name is Victor Pancratius. I'm leading the data science in astroinformatics and geoinformatics at MIT Haystack Observatory. And since this is an unconference format, I decided to unslide this talk. So let me just tell you a little bit about what we're doing. So we are...
Sorry, if people don't use this, they can't see you on the video. Or they can't hear you, sorry.
So we are working on artificial intelligence and computer-aided discovery to make new discoveries in data science. And I'm particularly interested to learn from you what are the challenges that you are facing right now with respect to data analysis, scalability, and so on. I think one particular frontier in artificial intelligence today is how to infuse domain knowledge into these searches and make these algorithms more aware about what they're finding. And eventually, we are going to progress to also generate theories and explanations for things that we find. And this sounds like science fiction, but it isn't. I can show you some examples of the work we've been doing so far with successes. And the data we've been looking so far in astronomy specifically is more related to exoplanet search, different wavelengths, time series, images generated by instruments. Feel free to talk to me if you have any questions. And I definitely want to talk to as many of you as possible to learn about your problems. Thank you very much.
I'm seeing slides from Hans. I don't know if I should. Are you Han? Yeah. Did you send me slides? Or do you want to do without slides? Yeah, I'll do without slides. Okay, perfect.
So, okay, excellent.
The microphone
is
right. Oh no, okay, wrong one. Is this?
I think that was the one there was.
Okay,
this one's it. Can you hear me?
Please go ahead.
Hello, everybody.
No, this one's it. This one. I didn't know there was another one. Let's get rid of that.
Hello. Okay. Hello, I'm Hans Baer. I'm a PhD student with Hubert Klar in the Max Planck Institute for Astronomy in Heidelberg. And yeah, unfortunately, I didn't come entirely prepared, but what I work on is the fragmentation of self-gravitating disks, and that is generally more in the planet formation category of astrophysics, but in recent work by myself and others, we found that the fragments in disks often are at the bare minimum of a few Jupiter masses, but oftentimes even larger than that. 50 Jupiter masses are larger, and so that gets into the star formation part of astrophysics. And so I did come prepared with a poster, so you can come and see me about that. But and I should clarify, I work with hydrodynamic simulations of disk fragmentation. But if you need some other way to recognize me, I may have a German name, Hans, but I have a strangely Utah accent. So thank you very much.
Thank you.
We forgot to mention that the posters will be put up at Pforzheimer House, and so for those of you who have them, just bring them with you over there. And we also forgot to mention that the meeting is called Star Formation Across the Universe, and it's perfectly fine to talk about very large scale or very small scale stuff, not just the in between.
Okay. So I will do the best I can to keep myself to 2 minutes. So here we go. But because everyone else was so good, which I'm not going to take advantage for, I promise, and try to keep us on schedule. So I'm Karin Öberg. My main interest is in the chemistry that's associated with planet formation, to understand how planets form, what kind of chemical compositions they end up with, what are the initial conditions for origins of life, and so on. But to understand that, you need to understand star formation and the chemistry that's going on during solar-type star formation, since that will be inherited into the protoplanetary disks where planets are forming. So one of the things that we recently have started doing is trying to do more unbiased searches of the more complex organic molecules around solar-type stars. And this is work led by Jenny Bergner, who's a PhD student here. And based on this and work from other groups and work on disks that we do ourselves, we can say that COMS, or these complex organic molecules, are common during low-mass star formation. We see them in at least half of our sources. They start showing up in very cold sources, and we also see them in disks. And this is not something, especially the COMS in the cold sources and in disks, are not that easy to explain with the current chemistry that we put into our astrochemistry models. So what we have been trying to do, and I want to really highlight the importance of laboratory work for understanding the chemistry of star and planet formation. So what we have been trying to do is to come up with new pathways that can allow you to form these organic molecules at really low temperatures. And I think we have two, one which I think is more promising than the other. One is to use acids and bases in ices to have them reform as larger organic molecules without any energy barrier. And the other one, which is most recent, is to that we have shown that you can insert excited atoms into existing molecules to form new molecules without a barrier. In this case, you can go from methane to methanol, which you can do down at basically 0 Kelvin. So this has no barrier. But if you want to understand how this is done more quantitatively, read the papers or ask me. And with that, we end the first set of introductory talks. So next up is Ilse Cleves, who will give our first framing talk. And she will talk about the small scale, and especially the chemistry that's associated with small scale star and planet formation, right?
Mm-hmm. Yes, that is correct.
And you probably want to attach the microphone to yourself.
Yeah. Wow, we're actually 2 minutes ahead already. I'll try not to ruin that. Okay. Okay, good morning, everyone. So this is the first longer framing talk. This talk is focused on the smaller scales, the AU scales, as well as molecules, some of the smallest scales. And it's definitely going to be biased towards the disk phase, the protoplanetary disk phase, as well as chemistry. Here is a laser pointer. So without further ado, sorry, 1 second. Okay, so while I'm setting this up, so a lot of the talk that I'll be giving today is really focusing on the results that have come out in the last sort of 5 years, or even 10 years, owing to recent facilities like Herschel and ALMA down here. And so I'll be discussing a lot of recent observational advances, as well as putting in a little bit of my own research, trying to mix these things together. in terms of the broader picture of the star and planet formation process, I'll be focusing down here on this third phase, the protoplanetary disk phase, where you've already dissipated your envelope. You're no longer feeding your protoplanetary disk. The accretion rate is much lower through the disk, and so the gas is primarily, it is accreting onto the star, but its more exciting and perhaps primary job here is forming planets. Got a relatively long lifetime to do this. Of course, we're seeing evidence of growth in much earlier stages now, so perhaps even this sort of idea needs to be reimagined a bit. And so some of the key questions we're really interested in is understanding how much of the chemistry, as Karin alluded to, from the earlier phases makes it through and is inherited into the disk phase and then into the planets forming out of this disk. We also want to know how the properties of this disk influence the actual outcome of planet formation, whether it's by core accretion processes or gravitational instability, as Hans discussed. And so the first question here is, of course, where does this disk composition originate? How much of it is inherited? How much of it is reprocessed through the disk phase? How does the physical environment within the disk affect the process of forming a planet? How does your temperature gradient? How does your velocity? How do your velocity fields? How do all of these factors change the outcome of planet formation? How many rocky planets do you form? How many gas giants do you form? And how do you actually do that? Also, how does the composition of this disk shape planet formation? So not only does the temperature and the typical physical processes we think about matter, but also the compositional properties. There have been studies that have shown that if you have ice-coated dust grains, they'll tend to stick together a little bit more favorably than a bare dust grain. And so maybe that enhances your process of growing grains into, hopefully, planets. Of course, this isn't true of all ice. Some ices don't have the same process, like CO2. And so we want to know how does these two questions, sort of where does this composition of the disk originate? So how does this composition, or where does the composition that feeds planets come from? And we want to know how do those planets form out of the disk itself. So the composition more broadly is set largely by irradiation from the star. So you have your central young T-Tauri or Herbig star, if you pick your favorite mass range. Your young star is heating the disk around it, and so you get temperature gradients where it's hotter close in, cooler further out, hotter in the surface, and cooler further down. The star is also emitting high-energy radiation like UV and X-rays, which can ionize the gas and impact the composition in that way. And so you set up this overall picture where you have ions at the very uppermost surface. Then once the radiation is more shielded by dust grains and also in some cases for the gas, like for CO and N2, which can self-shield and protect themselves, you form a molecular layer a little bit deeper in. And then as you get even deeper into the disk, where the reprocessed radiation that's heating the upper layers of the disk is diluted, you get a cooler core where the grains are now cold enough that molecules tend to hit the surface of the dust grain and form ice mantles and form sort of things like water, HCN, ammonia ice. And then as you get further away from the star, you can get ices like CO and N2. And so you get this gradient in the midplane owing to the binding energy of a given molecule to a grain. So these things are more tightly bound, so they tend to freeze out first. These things are more weakly bound, so you freeze them out much later. Oh, and we often call these things, these transition points in the midplane snow lines. You probably have heard of those. And so every molecule has a snow line in the most classical sense. Of course, that gets blurry if you start to mix ices together. What is your snow line? And also, you may notice it's not just a radial transition, but it's also this vertical transition. It's more like a snow surface, not so much a snow line. So just a brief overview of the sort of topics I'll be covering. We'll talk about the sort of the most fundamental parameter is estimating disk masses, what we're learning about abundances, volatile abundances in the disk for both oxygen and carbon. I'll discuss some recent work on understanding what's going on with nitrogen in disks, how this relates to some of the physical properties we're learning now with ALMA, and emphasizing the key role of understanding temperature in making all of the measurements above. So mass is this absolutely critical parameter. I mean, at the most basic level, your total amount of gas mass and dust mass sets your total amount of planet mass. No surprise. This was a press release image of the number. It was something like, it was 60 Jupiters for one disk from this press release image. So we want to understand mass, not only to understand how much planetary material you can form, but mass also changes the composition of the disk indirectly. So if you have a very massive disk, it's harder to fully heat. It tends to be cooler, and so you might end up with a more ice-rich disk. While if you have a low-mass disk, it's more permeable to radiation from the star, and so it can be a warmer disk, it can be a more overall ionized disk. And so you can actually fundamentally change the composition of the planets forming out of it based on the mass. So it can affect both your outcome, your total number of planets, but also what they look like. Historically, to do this, to measure mass, you've had a few options. The classical way of direct gas-to-gas measurement was using something like CO, where CO is the second most abundant molecule after H2. H2 we can't measure. It doesn't have a permanent dipole moment, and these disks are too cold to measure it directly. CO, unfortunately, because it's so abundant, it's optically thick, so you have to use things like 13CO or CH. This is not a new problem. This is not unique to disks in any way, of course. It's a cross-star formation in whole. But then you have to use a conversion factor. The interstellar CO abundance is something like 10 to the minus 4 per H2. And so then you can convert your CO mass and try and estimate a gas mass that way backwards. You can also do a similar thing where you now say, well, I can easily measure the millimeter emission coming off of these disks. And then you can assume a different conversion factor. Well, first you take your millimeter emission, you assume a temperature, then you have to assume an opacity, and then convert that to a dust mass. But then to get a gas mass, you have to assume a gas-to-dust ratio. So there's always this sort of conversion factor in the way. A similar way of getting masses is through dust, is through spectral energy distribution modeling. That sort of, it's typically unresolved. But it covers a broader wavelength range, and so you can sort of get the mass distribution in some. You can sometimes get the mass distribution a little bit better than just with millimeter emission. And then so all of these mechanisms or all these methods have caveats though. CO is actively involved in the chemistry. Perhaps it's one of the most active molecules in the chemistry. It reacts with basically everything because it's so abundant. It's also can be actively destroyed by photons from the star, and it can freeze out. Dust also has problems because, well, we're hoping this dust is actually going and making planets, right? And once it makes a planet, we can't see it anymore. Or even if it makes beyond centimeter-sized grains, if you start to make larger and larger bodies, it becomes invisible to us. And so both of these conversion factors are actually time-evolving. This is why it was so exciting just a few years ago, 4 years ago, when with Herschel, in this paper, it was reported the first detection of deuterated H2, HD, hydrogen deuteride. It's a beautiful detection shown here, non-detection of the 2-to-1 transition, so that actually tells you something about an upper limit of temperature. And so the nice thing about HD is that it still has a conversion factor, of course, but it's been really well characterized within the local bubble. And so we know the HD to H2 ratio pretty well. It's a couple 10 to the minus 5. It doesn't freeze out as early as CO. CO typically freezes out at 10K. HD can stay in the gas until sometimes 5 to perhaps as much as 7K, depending. And it doesn't actually get strongly chemically altered, at least based on models. I know there are different results there. At least in our models, we don't get more than a factor of 2 loss. So to get a mass within sort of a factor of 2 certainty, it would be excellent. We're not quite there yet, but that gives you an idea of why HD in many ways is a very useful tool. Let's see. Just recently, Melissa McClure reported the remainder of the HD detections that we have in disks. There are perhaps 2. These are the ones that are over 3 sigma detections. The rest are non-detections. And unfortunately, of course, Herschel's no longer with us, so we're not going to be getting any more of these anytime soon, unless, well, hopefully Sophia Hermes happens, which is in many ways the case for Hermes is actually to get these measurements, to get HD. in tens or maybe 100 disks. And so from these, if you take the 3 disks we have, the first one I showed you here, this one is TW Hydra. You'll be hearing about it more later. It's the closest disk to us. It's the best studied. We have gobs and gobs of data on this disk. It's staring at us face on at about, I guess Gaia now has it at 59 parsec. I have to keep revising the number in my mind. And so, yeah, it's staring at us about inclination of 7 and pretty close. So we've been studying it quite a bit. And then these two, DM Tau and GM Auriga, all of these are about solar mass stars within 20–30%. But if you take all 3 of these, you estimate the gas mass from HD, assuming a temperature structure, and then you, in turn, take their spectral energy distributions, their millimeter fluxes, and estimate their total dust mass, the global gas-to-dust ratio in these disks is all consistent with 100. The error here is a factor of 2 still, but that's pretty interesting. Gas-to-dust of 100. One thing I didn't point out is that this disk, TW Hydra, is about 8 or 10 million years old, and these are only a few million years old. They're in Taurus. So it's kind of odd to think about. In the meantime, there's been a lot of work done with ALMA surveying various star-forming regions. This one is Megan Ensdel's survey of lupus. Up here, this is a megaplot, I'm sorry. These are just objects ordered by dust mass. These are the lowest dust mass. These are the highest dust mass. And these would just have numbers down here, ID identifiers at the bottom. So there's nothing on the x-axis except just increasing dust mass. They also went after 13CO and C18O to derive gas masses with CO. And all of these points here are the gas mass, including the conversion factor of 10 to the well, they include a conversion factor that's model benchmarked. They ran a giant grid of models, so it includes freeze-out, it includes UV effects. And then based on this giant model grid of 13CO and C18O flux, they back out the gas masses of these disks. But the thing to point out here is that everything with a down-pointing triangle means neither were detected, 13CO nor C18O, so they couldn't get a gas mass. And then if they have an arrow plus an upper bar, that means 13CO was detected, but C18O wasn't. And then both double bars mean both were detected, so they can get a gas mass. And so that's a lot of non-detections in C18O and a lot of non-detections in 13CO. And if you plot along here what one Jupiter mass of mass looks like, right here, you would actually conclude that most of these disks could never form a Jupiter. So something's up here. Either these disks are extremely gas depleted or something is wrong with CO. And down here is just taking that ratio of gas from CO, dust mass, and here's 100. And you get this downward trend, but it's just the upward trend from the millimeter emission. And so this is interesting because, well, here we're getting sort of statistics in the population. HD, we only had those 3 sources. But it's telling us something is up with CO. And this was further, not confirmed, but backed up by this work by Menard et al. 2016, where they took the same lupus survey that I just showed you, but they also got really excellent X-shooter accretion rates shown on the y-axis. And so they have 2 plots here. One where they compare the gas mass from CO versus the accretion rate. And these things for a viscously evolving disk should be related. And then they compare the dust mass times 100, the interstellar gas-to-dust ratio, versus the accretion rate. And they find that there is no statistically significant relationship between the gas mass from CO and the accretion rate, so these things seem to be unrelated. And they also plot some dashed lines here, which would be if you take the total mass of gas in your disk divided by your accretion rate, what is the time scale for that gas to go away? And so up here, this is a line of 0.1 million years, 1 million years, and 3 million years. And you notice there's a lot of disks that are lying well above the sort of 3 million year line or even 1 million year line. So these disks have not enough mass in them to actually sustain the measured accretion rate. These disks shouldn't exist. They shouldn't be there. They should have dissipated long ago. And that's assuming the modern day accretion rate. It may have been higher, earlier. On the right, they do find it's definitely noisy. They claim, using the Cox hazard test, they find a probability of lower than 10 to the minus 4 of no correlation between the accretion rate and the gas from dust mass on the right. So they find a statistically significant correlation between these two. And if you put the same curves on here, you have a much larger number of disks falling below the 3 million year line than you do on the left. So the timescales seem to at least be more sensible. You have enough mass if you take your dust mass times 100 to sustain your accretion rate. So this is just sort of a thing to think about. It's a bit strange or maybe disconcerting, is how do we actually keep an interstellar gas-to-dust ratio in sources spanning a wide age range? Either we're not losing a lot of molecular gas, at least in the outer disk, and dust simultaneously, so you're not making rocky planets very efficiently or dissipating the disk itself, or you'd have to get these processes to go at the same time to maintain 100, which is also kind of, that would be very, that seems unlikely to me at least. But just something to think about, that these gas-to-dust ratios seem at least decently consistent with interstellar within a factor of 2, and so what does this mean for gas dissipation times and dust dissipation times, or planet formation times? So I have 30 minutes, right, for this? Okay, yeah, all right. So the additional beauty of getting this HD measurement means we can actually derive CO abundances in a couple of disks. This was a nice work by grad student Camber Schwartz out of University of Michigan, where she looked at TW Hydra. Here you can see how face-on it is. It's staring straight at us. And she measured the CO abundance versus radius, assuming a gas density profile. And she found that the abundance of CO never returned to the interstellar value of 10 to the minus 4 at any location in the disk, even inside of the sort of canonical CO snowline, which is here. You kind of see a bit of a bump. You get two different curves depending on which temperature profile you use, but at both extremes, you still never recover the interstellar CO abundance. So it's not just CO is freezing out everywhere and we're missing it. CO seems to be not returning even into the inner disk. The abundance of CO seems to be low everywhere. Mikhail Kama did some additional work with APEX, found that even, it wasn't just that CO was being photo-destroyed and turned into carbon, that the neutral carbon abundance was also low. So there seems to be something wrong with carbon. Not wrong, but carbon seems to be missing from the upper layers of the disk. This was interesting because there was an earlier detection reported with Herschel as well of cold water vapor being desorbed from the surface of the disk by UV light from the star. And the water abundance, I don't have a plot of it here, but that we should have detected that the peak of this line should have probably hit the sort of top of this slide. Had water been well mixed, oxygen been fully present in the upper layers of the disk. Typically, the process of photodesorption and freeze out, balancing that out, yields a water abundance of something like 10 to the minus 8. And the abundance of water seen was about over 1, less than 2 orders of magnitude below that. Factor of 40 to 80 of oxygen seemed to be depleted or missing from the surface. DM tau also has a similar amount of water reduction, less than or equal to about 50, given the upper limit in water measured there. And then if you start to actually compare now, you have these disks, you have TW Hydra, you have DM tau, you have water measurements in both, you have HD measurements in both, and you have carbon measurements in both. You seem to find that TW Hydra, the older disk, is more carbon poorer than DM tau. DM tau seems to be only about a factor of 8 carbon depleted, while TW Hydra is closer to about a factor of 50. So the idea, what's happening? Where is it going? Is it just gone, dissipating with the gas? What's happening here? The idea put forth by Mikhail Hogerheide was that if you have your disk, the star light is coming from this direction, I guess. This is your surface of your disk. If your disk is really, really well mixed, you are bringing up water ice coated grains into the surface. UV light's hitting that water ice. It's bringing back water to the gas phase, and that should be observable. So his idea was that these grains, these water ice coated grains, are sticking together more efficiently, and they're growing, and they're settling to the midplane below the UV layer, the extinction, the tau of 1 UV layer. And so the UV light that's hitting the surface of the disk is seeing pretty much bare grains because the water ice grains have grown and become shielded. Since then, Fujun Du published the remaining survey of Herschel water observations, and too complicated to go through here, but the main takeaway point is that there's a lot of upper limits. These were deep observations. Some of them were 10 hours with Herschel, and water still wasn't seen. So it's disconcerting. Where is that going to? This put some interesting. This has some interesting next stage ramifications. I don't know what the right. It's too early. I haven't had enough coffee. Ramifications for the physical nature of the disk. Mainly that you can't be taking your grains and recycling them back up efficiently from the midplane. You can't be returning your water to the surface by strong vertical mixing. Otherwise, we should have seen a lot more water with Herschel than we did, and we didn't see that. This was interesting in light of ALMA, recent ALMA work too, where the constraints that are being found via various means, whether folks have done image plane analysis, looking for residual turbulent mixing motions by first having to remove the Keplerian motion and remove the thermal broadening, but looking for residual turbulent motions. And so far, without getting into too much of the details here, they have been both claim that the values of turbulence have now, both measurements have been upper limits. So let's see, I think the Flaherty work was less than 10% of the sound speed on this original work. This one was 20% the sound speed. Kevin Flaherty's come out with a recent paper in 2017 where he's used a whole host of different tracers. This is really hard work. You have to really know your thermal structure to do this because you're trying to both fit for thermal structure and turbulent mixing. But trying to do this, Kevin finds turbulent residual velocities of less than, in some places, less than 5% of the sound speed, which is inconsistent with actual MHD-driven turbulence in disks. So that's kind of scary in its own sense. Another way that people have tried to measure turbulence is actually not using the gas at all, but using the dust. And this is a work by Christoph Pinty. Someone? No? Okay. I've never been able to say his name, and I can't ask him because it's been too long. I'm there right now. But here on the right is the actual data of HL tau. You see these nice rings. The rings are extremely symmetric, and so that he's able to put actual pretty good constraints on the amount of turbulent kicks those grains can be receiving to keep them flat. So that the thinness of these rings is less than an AU at 100 AU. It's like very thinner than a pancake. It's like a crepe, I guess. I don't know. And that he puts upper limits of this is the alpha, sorry for switching parlance, but a very low alpha of 3 × 10⁻⁴. This is in the midplane. So the other observations were gas, primarily from the surface. This is the midplane. Just shortly after, we also, this was work with Ted Bergen as well as Joel Kastner, observed C2H in TW Hydra, and it was, well, Joel Kastner reported it with the SMA, and it was extremely bright. Joel was actually able to even resolve the ring in C2H with the SMA. And this, there is noise. This is actual data on the sky, and you can kind of see the noise in here, but it's a really, really bright line. It was surprisingly bright, actually, when we got the data. But thinking back, actually, now that we know what we know from Herschel, is that C2H and other hydrocarbons are produced in abundance when you have very little oxygen sitting around. Oh yeah, I have a timer. I think I'm on time, kind of. I'll skip ahead to the exciting stuff. This is exciting. So everything's exciting. This is actually a totally natural outcome of the chemistry when you have lots of carbon running around relative to oxygen. When you're in an oxygen-depleted environment, the carbons want to go make CO, but they can't because there's no oxygen, so they go find each other and make friends and make C2H and C3H2. They're just like, they're noise bars on this. That's RMS, but it's still pretty wild. Excuse me. Recently, there have been some additional constraints now on nitrogen. So we have, early picture to summarize. Oxygen is very depleted. Carbon is also somewhat depleted, but not as badly as oxygen to make all those hydrocarbons. So here's nitrogen. Also with Herschel detected the first, and I think only, maybe one other, cold ammonia detection. I'm looking at the audience. I can't tell if there's any knowing looks. This was a grad student, Nico Salinas. He estimated the ammonia to water ratio using various toy distributions. Like this is what you'd expect sort of from a photodesorbed layer from the star, where what you're observing surface. This is like a different scenario where you have like lots of collisions between rocky bodies in the midplane, producing your abundance structure. We think this is probably more likely now. But from assuming that it follows a distribution that's in the surface, either compact or extended, you get an ammonia to water ratio of somewhere between 30 to sort of 80%, which is way higher than what you see in comets in Hale-Bopp, which is less than 1%. So it looks like the surface of the disk has this very high ammonia to water ratio, but maybe it's just all your ammonia sitting around, but your water's already left a long time ago, so creating an artificially high ratio in the surface. This was interesting because also recently the first organic was detected, disks by Karin Oberg. Sorry, no umlaut. I was in a hurry. The largest complex organic was methyl cyanide, and this was really surprising because it wasn't methanol. I mean, it was exciting that it was an organic, but more exciting to me at least that it wasn't methanol. Although methanol was found, it was just very low in abundance by Catherine Walsh. We're working now on trying to get additional nitrogen abundance constraints from another disk, IM Loop. This is a beautiful ALMA detection of HCN 3-2 with ALMA. That's the edge of the millimeter dust disk, and so it seems pretty well associated. The inner part's a false hole. You can ask me about it later if you're interested. So great, beautiful HCN detection. So let's go after H13CN because we want nitrogen abundances. And what do we see? A lot of nothing. It's a beautiful nothing. It's like a 3 millijansky noise floor nothing, but it's per beam, but it's really, really nothing. And so we asked, is nitrogen also depleted? What remains? This disk, we fortunately had just finished a massive effort to try and model the gas density and dust density distribution of this disk with ALMA. This was from last year. We had lots of CO transitions. We had beautiful images of the continuum. I believe there are more. Sean's getting more soon, I think, of even higher resolution observations. But these are just gorgeous. And based on this beautiful data, we actually constrain, using the dust mask because we don't have HD, we constrain the CO to be depleted by about a factor of 20. And the data were so good, we could constrain the external radiation field incident on the disk, assuming some line-of-sight dust opacities, which you can ask me about later if you're interested, or see the paper. To help us in this effort, and I have 1.5 minutes left, we had some additional observations of C2H, which is this molecule I told you all about that's very sensitive to the carbon to oxygen ratio. It forms in abundance when you have lots of carbon but not oxygen. These are two actual blended hyperfine pairs here. So there's actually 4 lines. These are actually quite nice detections too of C2H, the N equals 3-2. And so using a combination of these HCN detection, H13CN non-detection, and the C2H transitions, we were able to constrain, sorry, no fun mega figure yet, still in progress, but we could constrain that the water was depleted by roughly a factor of 50 to 100, CO somewhere between 10 to 30, we favored 20 in the first paper, and then nitrogen is depleted, but not like by a whole lot. It's actually only depleted by between 2 to 10. So you seem to have this sequential, oxygen's very depleted in the disk, carbon's mildly depleted, nitrogen's slightly depleted, but not by a lot. And also we found that based on the absolute best fit of our current grid is nitrogen depletion of a factor of 5 and a low cosmic rate, 10 to the minus 19, which is lower than the canonical value of 10 to the minus 17, but consistent with our earlier measurement from TW Hydra. That's my other favorite thing to talk about is ionization, but I don't have time here. But keep in mind, all our measurements of depletion and what am I talking about, they're coming from the surface. This is where these molecules are emitting from. And we're having to infer a lot from models what's going on in the midplane. what we think is happening is that, I'll skip ahead. I made this animation a long time ago, so I always have to show it. Oops. We think that the ice-coated grains are tending to settle in and drift inward, and so you end up with what looks like a volatile pore surface, but you might have a volatile enriched midplane. It depends on what the fate of these particles are. Do they fall into the star? Do they get trapped into rings? What happens? And so because I'm running out of time, I'll skip ahead a bit and give you sort of our overview. So we think oxygen is sort of being quickly sequestered from the surface, coming from inherited from the earlier phase. Those grains are growing rather quickly, and so they're the first thing. Oxygen is the first thing to go. So that's why it looks like it's the most depleted. It takes some time to deplete the carbon, and also even more time to deplete the nitrogen from the surface. So you have this sort of inherently evolving volatile distribution from the upper layers, where it's at the most basic level, at the heart, it's linked to the evolution of the dust grains. Where are those dust grains taking volatiles, and where are they hiding them or removing them to? So that's also kind of terrifying from the perspective of being a modeler, because we now have to think about this very much linked and time-evolving process, and also understand the process of dust growth and drift even better to understand the chemistry. And since I'll skip ahead since I don't have time, but here is my summary slide. So we're seeing in many disks the gas-to-dust ratio is consistent with roughly 100 within a factor of 2. There's the error. We're seeing time-evolving and spatially evolving volatile distributions. And we see sort of the sequence between oxygen, carbon, and nitrogen. Starting to see that disks aren't very turbulent. They seem pretty dang Keplerian, which I guess it's boring to some, but interesting from how do these disks accrete standpoint. But I should point out that both of these are still limited number statistics. We've only been able to do these studies on a handful of disks, at most 5, and for the turbulence at most 3. So that's the timer? Okay. Yeah, I'm done basically. Low ionization in at least one disk, that's the published one, now perhaps 2. With the new IM Loop paper, we'll be following up with an actual detailed ionization study of the disk with spatial information. And it seems like dust transport is truly central to the story of understanding the composition of disks. Okay. With that, thank you.
So we have now about 10-15 minutes for discussions, comments, questions for Ilse. Other people want to chime in. So Ilse, stay wired up, and the rest of you start asking questions. So Alyssa, I guess the first one.
When I was thinking about how would you see what was inside the disk, that you published, are there any binaries that maybe rip the disks apart a little bit where you could see that?
Oh no, Joey's not here. Joey has a really neat system of two. It looks like a disk that's being ripped apart by binaries. Yeah. I don't know I think it's pretty low mass, so I don't know what we could do about the composition, but I don't know. It's an interesting idea. I don't know how that would also then affect the chemistry in some way. Having look at sure, galaxy people. Yeah, I don't know. Yeah, I mean, there are some studies to get at the solid component. Yurikawa did this, looking at some disks that are at the perfect inclination that you can. I think it was ice observations with Akari, looking at the solid state features and absorption, and she got some, I think, water, but I don't know what else. But you have to have very specific geometries to get that, because you need your stars, your back candle. You need to be looking through your disk, but you don't want to look through your disk perfectly edge on. So it's because otherwise then there's too much extinction, so you don't get to see the star at all. So there are a few systems, but they're the chance alignment systems.
You mentioned that water is depleted, that the carbon monoxide is depleted, and then you say the oxygen is gone. Where did it go?
Not totally gone, but we detected the water there, but it was very weak. So the idea we're using the term sequestering. That's our own theory. There are other theories out there where it's going via the grains. The grains are carrying it into the midplane and towards the inner disk, into the region where we can't actually observe it directly. So it's in the ice phase, well, until you cross, the water snow line. So it's not gone, but it's hidden. Maybe that's the better term to use.
And then the question is if it's getting up again and you can see if it's JWST or not.
Yeah, that would we'd love to know. Yeah.
Thomas.
I had a comment on the turbulence we worked on as well, and you're absolutely right. It's a very hard problem because you really have to get the thermal structure right. And I'm a bit skeptical of this parameterized models. I think you have to do it directly with your molecules.
Yeah.
But what we now have seen when we went back to modular INCS data for TWI, that there may also be a non-Keplerian contribution, which is actually related to the disk structure, which practically means that you have to be very careful to assume that it's all Keplerian, you just subtract that. And at the end, when we did this exercise, then there was practically no turbulence left at all.
So are you suggesting a warp in the inner disk? Yeah.
So
wow.
there's some evidence for that, I would say. And, which really tells you that they are very low turbulent disks, and now TWI is relatively old, but that holds for other objects. We may have to revise our picture completely. I mean, of course, one alternative is that the momentum is transported by winds, and we also see some evidence for that. So I think that's interesting territory.
The wind model is definitely coming back into fashion with a laminar core, exactly. And this is actually an old figure because Ryan sent me new ones. So Ryan Loomis is a PhD student with Karin working here. Speaking of temperatures derived directly from data, he's doing using multi-transition. This is soon to be submitted work. I wrote that at the top. Hopefully submitted soon. I don't know. But he's fitting a load of 7 transitions, also a load of transitions of methyl cyanide, CH3CN, and doing spatial rotational diagram analysis. Or he's getting rotational temperatures. The beam here is large. I think it was about 50 AU. So we don't actually think the temperature is 30 K at 0 because there is a beam smearing effect here. But he's starting to get direct temperatures from multi-transition analysis from methyl cyanide. This is also TW Hydra, and the temperature is, well, you can see here it's low. It's like 30 K. I had to cut this part out of the talk, but some of the 2 models that have been used to explain the disk in the past. Here's Mikhail Kama. This is Uma Gorty's model that was published in the initial detection of HD. If you look at the same spot where he's constraining the temperature to 35-ish K, the temperatures of both of these models is well over 50 and closer to 100 K. So these 2 disks are significantly hotter, which means that in some of the model analyses, the temperatures that people are using are actually too high. So I just wanted to point out temperature is important. Yeah, mostly UV from the star, photoelectric effect, photoelectric heating. Yeah, in both of these. They're totally different models, and equally terrible to read. Color schemes, I don't take credit for it, but yeah, but oh yeah.
Any other questions or comments on anything disk or chemistry related?
I shouldn't do this, but I have one more.
Go for it. We have like extra time.
So
5 more minutes.
Thomas was just telling us that maybe there's a warp and maybe it's not.
Yeah.
What if there's still some accretion onto the disk, which would change the
Like a remnant envelope.
chemistry and the dynamics and the temperature? Like, do we know anything about beyond the edge of what's in the gamma?
For the turbulence measurements, those are the places that we know the best, I guess, so we actually don't know what's going on in the inner disk because of the resolution limits. So that's the part of the disk that seems to be pretty low in turbulence, and has the low temperatures. It gets noisy, but
sitting there alone enough, not surrounded by something that's the remnant of some
I see.
blob of gas that they formed out of that we don't care about anything outside of the edge of what we're calling the disk.
Some yes, some no. Like TW Hydra is pretty alone. Many of these disks are pretty alone. We saw a remnant fluffiness, also scientific, to IM loop. Where is it? There you are. No. So it seemed like there was excess material in the outer disk. So maybe, you know, the gas falls off. We were assuming power law plus exponential taper following the self-similarity solution. Maybe that's put gas out there. But it seemed at least that power law plus exponential taper fit most of the disk for the inner 600 AU. But from 600 to 1,000 AU, there was a lot of fluff. And there was also a recent work by Christoph Pinton. Not again. I've got to learn it. Are you recording and posting this?
Oh, yeah.
Oh, God. Don't show him this, please. This is embarrassing. But I think they also suggested that there's maybe a velocity change. Stefano Facchini thinks it's a wind coming off of the outer disk. So but it's very young. This is probably 0.5 to 1 mega years old is the most recent estimate. But yeah, most of the disks I talked about here are isolated loners that are easy to study because they're close by, but in that sense they're also isolated. But yeah, it could be, yeah.
Well, I am very happy to keep us on schedule, so if there are no more comments, let's thank Ilse again. Introductory talks, and I think David, you're first. We can. Here you are. So there's the Mac. Do you have slides?
I have a slide.
Okay,
Yeah.
then we will set those up.
There we go.
Okay, please.
All right, so I'm David Wilner. I'm an astronomer here at the CFA. I've worked on many different aspects of star and planet formation, mostly using the technique of radio interferometry. My recent interest has been in studying debris disks with this technique. With my latest student, Meredith McGregor, who made this beautiful image, and other collaborators. Debris disks are kind of the end state of disk evolution. This is short-lived dust around main sequence stars, which we infer is replenished from the collisions of larger bodies in the system, analogous to comets or asteroids. So the relevance of the millimeter wavelengths is that the large particles that dominate the emission at long wavelengths most faithfully trace those larger bodies because they're relatively unaffected by radiation forces and stellar winds, unlike small grains you might see in the optical that are blown around the system. So these are interesting for a lot of reasons, but mostly to get at the remnant of planet formation of the planetesimals, which probably exist at late times, mostly in stable regions like belts and resonances. So one can look at the structure of these things with the high resolution provided by interferometry to hopefully probe planet-disk interactions. This is especially neat, I think, to look at the possibility of wide separation long period planets, because those are the ones that are really hard to detect with all the methods that require seeing many orbits, like transits or radial velocities. But they're also the planets that are potentially most amenable ultimately to direct imaging because they're at wide separations. And another cool thing that's turned up in some of these investigations is the detection of exocometary molecular gas, which is giving a window into the composition of the ices of these remnants of planet formation. Okay, that's all.
Charles, you're next. Yes, so next up is Charles Law, who did his senior thesis with me.
All right, hello everybody. I'm Charles Law. Okay, so I'm going to talk a little bit about carbon chains. I did this work with Karen Oberg. You might recognize this plot, which is the same IRAM 16 source sample that was shown, but instead of the comms, I'm looking at the carbon chains. Carbon chains serve as a reservoir of a reactive organic material during star and planet formation, and they've been observed towards several low-mass young stellar objects. But the typical carbon chain abundances and their chemical relations in these sources are poorly constrained. So that was sort of the motivation behind this. We're also looking to see the chemical origins of carbon chains. Is it simply inheritance from the cold cloud phase, or are we seeing some active process, such as the warm carbon chain chemistry, that's producing new carbon chains in these deeply embedded protostars? So here's the results. The blue bars in the bar plot here show the median column densities and abundances in the carbon chains that we looked at. The blue bars are showing where we take into account the upper limits, which become more significant for larger carbon chains like C3s or HC5N. We detected only about 40% in 40% of our sources. We also compare our median column densities and abundances against these WCCC sources. These are sources that have excess carbon chains, and we find in all of our sources that they're underabundant compared to these. So we don't see any new warm carbon chain sources in our particular sample. The main takeaway from this work was that we see carbon chains are common at this stage of protostar evolution. So there's a lot of carbon chains in these deeply embedded protostars, and we don't see any new candidates for warm carbon chain chemistry. They're all relatively underabundant, both from the observations shown here and from the model expectations. Right.
Thank you. Dima, you're, I think, our final introductory speaker for the morning. So you can just hold the microphone.
Okay. Is it fine like that? Yes, I have of slides. All right, I'm Dmitry Semenov. I'm from Max Planck Institute for Astronomy. So I'm astrochemist. My main topic of interest is the chemistry in protoplanetary disks, but I also study chemistry in high mass and low mass star-forming regions. So the basic idea is to try to use the power of molecular lines to understand physics. It's something pretty much what Ilse was talking about. But also understanding chemical complexity that was available during the formation of planet, and especially, for example, how much organics were there, where the comets formed or asteroids formed or the Earth has formed. And if you think about it too much, as I do sometimes, then the next question, logical question, is whether these things could have been of any relevance to the origin of life. And this is a very slippery slope because the origin of life is a very complicated topic. It's like astrobiology or something very, very interdisciplinary. But it's something that I also liked to think about. And then the last year I finally also did a publication with Canadians on the origin of light topic, the first one, hopefully not the last one. And that's on the next slide. It's in essence, the question you may ask, what happens during the very earlier phases of the Earth's evolution, where it is just formed and the surface has solidified, providing the first conditions at which life could have emerged. And there was a lot of things falling onto the Earth at that time, bringing water and carbon, but in different forms. First, there were interplanetary dust particles, or some very small particles slowly raining down from the atmosphere. But there were also a lot of bombardments by asteroids or meteorites. And we developed the first model where we followed the destiny of materials that would be brought by carbonaceous IDPs or carbonaceous meteorite into the warm little pond, the idea that goes back to Darwin. And we followed, basically the entire extraction and loss terms for amino acids that could have been delivered. And what we found out in our PNNS papers, that it seems, unlike the original Chiba and Sagan idea, that it were not IDPs that were important in that aspect. It's most likely that carbonaceous meteorites, that some rare event when a piece of meteorite falls into a pond and amino acids got dissolved. And if we have wet and dry cycling, you can accumulate amino acids and start polymerizing them, going the first steps towards the RNA world. So we can discuss about it later during the meeting. Okay, thank you.
Thank you. Okay, so the last talk before our first break is Hope, who will give a research talk on droplets. I'll give you a 2-minute warning.
Yeah, sure. Thanks.
Hope is plugging that in just to remind you, some people came a little late. When Hope is done, before you go over, if you have an idea for an unconference, write it down on these pieces of paper and we'll bring them over for the talk. And if you don't know where you're going, just follow one of the local organizers.
All right. So Hope Chen here. I'm a PhD student here at Harvard with Alyssa. And just FYI, I'm also in the job market. So I'm going to talk about droplets, and I'm going to, so it's a work, it's a collaboration with Jaime Pineda and Alyssa Goodman and all these fantastic people here. Since I only have 9 minutes, so I'm going to go a little bit fast, but do ask questions at the end. All right. So, so droplets, what are they? They are pressure confined. Why is it blinking? Okay. Anyway, I hope it's fine. All right. So it's pressure confined and it's thermalized, and it's they have sizes smaller than 0.1 parsec. But before I tell you all about this amazing thing, let's take a step back and talk about something that might be more familiar to some of you. So it's coherent cores, it's dense structures with subsonic line width, and Alyssa Goodman here proposed that these kind of coherent cores exist based on a bunch of ammonia observation as well as C18O for some of them. And then these coherent cores are often marked by this transition from the turbulent line width outside of a coherent core to the subsonic line width inside, and the line width probably stays the same all the way to the center of these cores. A coherent core and the transition to coherence is directly observed in 2010 by Jaime Pineda. This is the line width map. So the lighter means that the line width is smaller, and that is where the thermal component of your velocity dispersion is equal to the non-thermal component. So everything inside is subsonic, and you see this transition from supersonic line width all the way inside. All right, and this kind of coherent cores are often ammonia bright as well. So Jaime did this observation using VLA of ammonia hyperfine line emission, and here it's showing the ammonia peak brightness, and you can see it's not too different from all the previous works that Phil has done, that Alyssa has done in the 90s of ammonia bright clumps of materials. And here comes our droplets. So using our new GBT observations of nearby clouds, that's from the GBT ammonia survey or gas, I'm able to resolve the structures inside because IL-1688 is about 3 times as closer than Perseus. So even with the same GBT, I'm able to resolve out finer structures inside the molecular clouds. And these two maps are to scale, so to physical scale. So you can see that immediately we see this kind of transition from the turbulence to subsonic inside, and there are many of them. And when you compare them, the coherent cores in B5 is not unlike a string of these kinds of droplets. And again, when identifying the droplets, I make sure that they are ammonia bright as well, so that they are at least some kind of condensation of gas and material and hopefully by doing so, I can make sure that these are real stuff, not just some line of sight effect. And in fact, with the very low line width, you're almost sure that these are not accidental, over brightness alone because of the line of sight effect. All right, so I hope that I've convinced you that droplets are small. So if I flip back, so this is the 0.1 parsec bar, and up there as well, and it's much smaller than what was expected of a coherent core before. Now I'm gonna convince you that they are thermalized as well. So we generally have this picture of star formation. First we have this molecular clouds, and then they start collapse. As they collapse, the size becomes smaller and smaller. We increase mass by accretion as well. And then somehow, because the initial material is very turbulent, so there must be some mechanism to strip off the turbulence which was there in the beginning. And I'm not going into details about that mechanism, but you have this picture, and it's bestly demonstrated on a Larson's plot. So on the y-axis, you have the mass. On the x-axis, you have the size. And then the white circles are the ammonia clumps in Odysseus works. And then there we have the coherent core in B5 as a cross. And then all the droplets are tiny and very low mass as well. So as you can see, the lowest mass is around 0.1 solar mass. So these are not your typical core that monolithically form a star or stars. And then when you look at the line width or velocity dispersion size plot, you immediately notice that all of these cores all of these structures are subsonic. So they dip below this, what you would expect when the thermal component of your velocity dispersion equals the non-thermal component, and then even below that. So these structures or droplets are really, so they have reached this final stage of the stripping off of the initial turbulence, and they are fairly subsonic and quiescent, as some people would say. All right, so I hope by showing you that, I've also convinced you that these droplets are thermalized. And then I'm gonna use virial analysis to try to convince you that these droplets are pressure confined. First of all, let's take a look at equations. Right, so in this equation, on the left-hand side, you have the confinement. The first term is gravity. The second term is what we call turbulent pressure. It's basically the pressure of the turbulence, the more turbulent material from outside of a droplet or a coherent core exerting on the surface of this subsonic core, right? And on the right-hand side, you have the traditional kinetic support, and you can mess around and get a factor of 2 difference, but I'm using what's defined in these 2 papers. And if you disregard the turbulent term for a moment, you get the traditional virial analysis, and you can get virial alpha, for example, from that. And that's what this plot is showing here. So on the x-axis, you have the kinetic support. On the y-axis, you have the gravitational potential. And you immediately notice, so the upper part of your plot, of this plot, is where structures are expected to be bound if there are only these 2 forces in action. And then the lower part is unbound, and you see all the droplets are gravitationally unbound. But what if I compare the right. So actually, when you see this trend, so I'm going to put this as a reference. This trend represents a model of constant volume density, a core from the smallest to highest. So it's actually fairly consistent with this constant or uniform density of a spherical structure, right? And then when you compare the turbulent pressure to the kinetic support, the droplets immediately goes upwards to where you would expect equilibrium between these two forces. So since they are not bound gravitationally, it's more likely that these structures are bound by the turbulent pressure from the outside or confined. And then when you combine the gravitational term with the turbulent term, you get this term. So the large scale are still gravitationally bound. They are gonna collapse. And then when you go to the scale of these droplets, they are mostly pressure confined. And you might start to wonder, like, is there something wrong with, because ammonia, as we know, is tracing a fairly small range of density. But here I put on Charlie's previous results, identifying objects using only the extinction map and getting the velocity dispersion, not just from ammonia, but from C18O as well. You get the same trend. And then you start to wonder, is there something wrong with this kind of theory analysis that always gives you this trend? But no, if you look at the JCMT cores in Orion, which is identified on the Scuba 2 maps, density maps, even though there's an overlap, a majority of the JCMT cores actually lies way outside of this constant density trend. It's even clearer when you look at the compare the turbulent pressure with the kinetic support. All the ammonia structures, together with the structures in pipe, they are thermalized, they are pressure confined, but not the JCMT cores in Orion. And this is the full comparison visual analysis. So, all right, so I hope I've convinced you that these structures are pressure confined, thermalized, and they are smaller than 0.1 parsec. But what are they? I think, this is just my guess, I think it represents the final stage of structure formation in molecular clouds. So it's the smallest scale. And beyond that, you are gonna get formation of disk inside, you're gonna get seeds inside, they may form star. So what are they gonna do in terms of star formation? So because these structures have extremely low mass, so they are not going to form a main sequence star by themselves. So the guess is that maybe they are gonna merge to form a main sequence star, maybe by itself, with some disturbance inside, it's gonna collapse to form a brown dwarf. Or maybe when the external pressure disappears, they are gonna evaporate because the confinement is mostly due to that pressure. And when there's no more pressure, they are gonna evaporate. So before I start taking questions, I'm gonna put Jaime's VOA observation of ammonia. And what he found was that inside this coherent core, there are actually seeds start to form stars. And these seeds, even though they are similar in size to droplets, they are much, much more gravitationally bound, and they have higher mass than you would expect from this trend. So I'll leave it there, and I can start taking questions.
Thank you. So questions for Hope, and I see one over there.
Yeah.
Are there any known lasers associated with droplets nearby, and do you have an estimate of the lifetime of an individual droplet?
So by the droplets, the droplet themselves, you're asking about the lifetime of the droplet, right?
And are there any class 0 or class 1?
Right. So there are. So these three are fairly stardust, or we don't see any according to C2D catalog. And these three actually have stars, at least along line of sight within that boundary. So we actually see an array of these kind of structures with or without stars inside. Yeah. Phil.
I hope if you take a pressure-bound isothermal sphere model and go to the state where it's critically bound, and then start turning down the mass, what is well known is that you then become more nearly uniform
Right.
So this sounds a lot like what you're describing.
Yeah.
Have you compared the properties to what you would expect?
I have not compared with an isothermal model, but that's also the sense I'm getting from this kind of virial analysis, because as you can see, all these structures are well within that equilibrium range. So it seems like this kinetic support is becoming quieter and quieter, as well as because they are smaller, so the total pressure exerted on the surface is smaller as well. So they're kind of like in this sort of equilibrium states and becoming smaller. I agree, but yeah, a comparison with the isothermal model would be reasonable. See.
So presumably these droplets live in a very dynamical cloud,
right?
Where you can have accretion onto the droplets. And looking at this in a snapshot, I'm wondering if the next step plan is to compare this with simulations where you get the dynamical principle as well.
Yeah, I would love to, but as I'm sure Blakesy would know, that there has not been a very clear. Or maybe enlighten me if I'm wrong. There has not been a very clear evidence of a very strict coherent-like structure with this kind of transition to coherence from simulation with like proper synthetics observation. Is that?
It's true, but I mean, another thing you can do with the simulation is to tease out the line of sight effect, because you're calculating all these quantities.
Right. Yeah. So sure. Yeah. So I think that's totally a reasonable next step to do, to see what's in the 3D, or whether or not the 3D velocity dispersion actually. Yeah. Yeah. I agree.
So we have two more questions. So first and then her.
Okay. So your analysis ignore magnetic fields, right? So if you assume a lot of mean strengths in the typical clouds like this, and how much will change your analysis?
I honestly do not know. So I think it's no, it totally makes sense to add a magnetic field term in this. So I cannot give you an estimate out of my head, but yeah.
You could just assume it was equal to the kinetic, and then it would just change that by a factor 2, and that's not very much.
Right. So yeah, I think there's also some kind of equipartition between these terms as well. That's the sense I got when I do this analysis, but I'm not sure how. I need to do more work to make sure that that's actually the case here.
And then this morning's last question from Eric.
So in this serial analysis, one supposes that there's a surface pressure. Do you have any idea of what the surface is, or what the pressure is, or how the pressure is transmitted to the core?
Right. So the idea here is that in the original idea about coherent core is that the density profile of the outside and the inside are different. So the density is steeper inside. So you see this transition there, and then the decrease in line width is also different. So it may be a parallel decrease from all the way to the surface, but then it stays fairly uniform, and that may be much like a isothermal model. So I would say that observationally, empirically, there is an very clear definition of where the surface is. And I think that's where you have the more turbulent material and the already quiet or like subsonic material, and the boundary between these two material is where I define as the surface, and where I think would be a reasonable way to look at the virial analysis.
Okay, so I'll take one last question from here, and then I think we're going to call this morning's session.
So I guess it seems like it's also kind of give you an idea of like how cores can be built up. So can you give you an idea of like kind of like competitive accretion between cores?
Yeah, I agree. Yeah, so when you look back the first thing you notice is that the size here, I maybe have it somewhere. Yeah, so it's 0.0, so it's sub 1 point parsec. And that's also where, when Larsen did his first analysis of standard multiplicity, that's a characteristic length scale that he found. I think he found like something like 0.04 parsec. And that's very similar. So I totally agree that, competitive aggression or merging or like these droplets, rotating around each other could totally be what's causing the later on the characteristics of standard populations.
What are the relative velocities? I mean, you should know that.
Right. So.
I mean, we never have seen that these objects are moving around like hell.
That's kind of true, but we only have line of sight information. But with that, so this is the line of sight velocity, and you see some of for some of them the line of sight velocity is actually very different from what is the system velocity of the clouds by up to like 1 kilometers per second. So I would say that the system velocity of each of these droplets is very different from each other. There could be relative velocity moving in and out. But of course, this is just a snapshot, and there's no way to actually know whether or not they are like doing this, they are coming together, or over the next, I say, tens of thousands of years.
It's interesting though, because in B5, in Jaime's latest B5 paper, the Nature paper, he shows that the relative velocities of those little pieces is tiny compared to each other. And then if you then look at the properties of the submillimeter sources, he derives a likely age for that cluster of only 40,000 years. And in that super short time, they have no chance of interaction. So
yeah, that's true.
And so, but that's a really interesting question.
Yeah.
I personally think that there's like a network of stuff which we can see connecting all those things, and that there's still flow from the bigger scale things onto the smaller scale things.
So we are at 10:42, so I'm going to call this the conference part of this morning to an end. I'm going to channel Alyssa, and if you were inspired, as you should have been, by any of the excellent talks or introductions this morning to come up with a topic you wanted to see further, maybe you didn't get to ask a question that you wanted to ask, please put it on to the nice spreadsheet that's in here. And then I think it's just to follow the LOC to lead us to...
So we're not leaving until at least 5 people are